Beneath the rolling surface of the ocean, far below the reach of waves and weather, lies a world unlike any other on Earth. It is silent, it is cold, and it is crushing. As you descend, sunlight fades to blue, then to nothing at all. At just a few hundred meters, photosynthesis dies. By 1,000 meters, the darkness is complete. And with every meter downward, the pressure increases, not gradually, but relentlessly, until the water presses with a force strong enough to buckle steel. This is not an environment meant for life, and yet life thrives here. Not only does it survive, in many cases, it grows to impossible sizes. Creatures that should be small become massive. Bodies stretch, thicken, expand. Shrimp grow larger than your forearm. Jellyfish widen beyond the size of cars. Squid reach the length of buses. This phenomenon has a name: deep sea gigantism. For decades, scientists have known it exists. But why it happens, why the deepest, coldest, most food-starved environment on the planet produces giants, remains one of the ocean's greatest mysteries. To understand it, we need to descend, a vertical world. The ocean is not one habitat, it is a vertical planet. Near the surface lies the epipelagic zone, the sunlit layer where almost all familiar marine life exists. Coral reefs, schools of fish, bright colors, fast movement, energy everywhere. Below it is the mesopelagic, the twilight zone. Light dims, colors disappear. Creatures begin to glow instead, producing their own light through bioluminescence. At 1,000 meters, sunlight vanishes completely. You have entered the midnight zone. From here downward, the ocean becomes alien. Temperatures hover just above freezing. Pressure rises to hundreds of times what we experience on land. Food is scarce. And yet, this is where gigantism begins to appear. Again and again, across unrelated species. Not just once. Not just accidentally, but as a pattern. The giants are real. Deep sea gigantism is not myth or exaggeration. It is documented. Take the giant isopod. In shallow water, its relatives are tiny pill bugs, barely a centimeter long. But in the abyss, the same body plan scales up dramatically. Some giant isopods reach half a meter in length and weigh over a kilogram. They roam the seafloor like armored tanks, scavenging whatever scraps drift down from above. Then there is the Japanese spider crab. Its body is modest, but its legs stretch nearly 4 meters from claw to claw. The widest leg span of any arthropod on Earth. It moves slowly across the seabed like a machine from another age, too large for most predators to bother attacking. In open water, the giants grow even stranger. The colossal squid, the largest invertebrate ever known, lurks in the deep Southern Ocean. It is shorter than the giant squid, but far heavier, weighing over 500 kilograms, with eyes the size of basketballs, the largest in the animal kingdom. Those eyes are not for spectacle. In total darkness, size means survival. Even small animals follow this pattern. Amphipods, normally tiny shrimp-like crustaceans, grow to over 30 centimeters in the deepest trenches. Something usually smaller than your fingernail becomes the size of a guinea pig. Jellyfish, too, expand into ghostly giants. The big red jellyfish drifts with a bell over a meter wide. lacking tentacles entirely. Instead, it uses thick, fleshy arms to capture prey, floating like a slow-moving balloon in the void. And at hydrothermal vents, where toxic chemicals pour from the seafloor, tube worms grow over 2 meters long, thriving without mouths or stomachs, surviving entirely through symbiotic bacteria inside their bodies. These are not isolated curiosities, they are clues. A world of scarcity. At first glance, gigantism makes no sense here. The deep sea is not abundant. It is a desert. Below the reach of sunlight, there are no plants, no algae, no constant energy source. Instead, most life depends on what drifts down from above. A slow, delicate rain of organic debris known as marine snow. Tiny fragments of dead plankton, fecal pellets, bits of decaying tissue. By the time this snow reaches the abyss, most of its energy has already been consumed by animals higher up. What remains is barely enough to survive. Occasionally, something larger falls, a dead fish, a squid, a whale. These food falls are rare, but when they occur, they can sustain entire communities for months or even years. In the deep sea, feast and famine are not metaphors. They are reality. So why grow large in a place where food is so scarce? The answer begins with physics. Slow is strong. In the deep sea, temperatures rarely rise above 4 degrees Celsius. Cold changes everything. Chemical reactions slow down, metabolism drops, movement becomes expensive. For most animals, this would be a disadvantage, but in an environment where food arrives unpredictably, a slow metabolism is a gift. Large animals burn less energy per unit of body mass than small ones. This principle, known as Kleiber's law, means that doubling an animal's size does not double its energy needs. In fact, larger bodies are more efficient. A colossal squid weighing hundreds of kilograms may need only a few dozen calories per day. One large meal can sustain it for months. A giant isopod can survive for years without eating. Size allows energy storage, fat, tissue, reserves that carry animals through long periods of starvation. It allows patience, and patience is survival in the deep. Cold water holds more dissolved oxygen than warm water. This matters. As animals grow larger, delivering oxygen to every cell becomes more difficult. In warm, shallow seas, oxygen availability limits body size. Grow too large and your tissues suffocate. But in the cold depths, oxygen is abundant. Cells can support more mass. Circulation systems can scale up. The usual constraints weaken. This is why gigantism is especially common in cold regions, not only in the deep sea, but also in polar waters, where starfish, sponges, and worms grow to enormous sizes compared to their tropical relatives. Size becomes possible because oxygen allows it. Pressure is not the enemy. To humans, pressure is terrifying. At 4 kilometers down, the ocean presses with over 400 atmospheres of force, enough to crush submarines and shatter bone. But deep sea animals are not crushed. Most are composed largely of water, making them incompressible. Their cells are adapted to function normally under extreme pressure. In fact, pressure may even favor larger bodies. Smaller animals have a higher surface area to volume ratio, meaning pressure affects more of their cells directly. Larger animals distribute pressure across greater internal volume, potentially reducing cellular stress. Pressure does not stop gigantism, it may encourage it. Predators exist in the deep, but they are fewer than in shallow waters. There are no reef sharks here, no dolphins, no fast pack-hunting fish. Instead, predators are specialists. Ambush hunters like anglerfish, dragonfish, and gulper eels. They rely on patience, not speed. In such an environment, size becomes defense. A giant isopod is too armored to crush easily. A massive jellyfish is too bulky and toxic to bother with. A colossal squid is capable of fighting back, its tentacles lined with rotating hooks designed to tear flesh. Even sperm whales bear scars from these encounters. When predators are rare, the evolutionary pressure to stay small and fast weakens. Animals no longer need to hide in crevices or dart away constantly. Growing large becomes safer than staying small. This is known as predation release, and it plays a major role in deep-sea gigantism. Time moves differently. The deep sea is ancient, not just old in geological time, but stable. Surface oceans fluctuate constantly: seasons, storms, temperature swings, changing currents. But the deep remains almost unchanged for millions of years. This stability allows evolution to slow down. Many deep-sea creatures are living fossils, lineages that have barely changed since the age of dinosaurs. The giant isopod's ancestors crawled the seafloor long before humans existed. When environments are stable, life can afford to grow slowly, mature late, and live long. Nowhere is this clearer than in the Greenland shark. Living in cold, deep Arctic waters, it grows to over 7 meters long. It moves slowly, it eats opportunistically, and it lives longer than any vertebrate known. Radiocarbon dating of its eye tissue suggests some individuals are over 400 years old. They do not even reach sexual maturity until around 150 years. At depths beyond 6,000 meters lies the Hadal Zone, trenches so deep that even marine snow barely reaches them. The pressure here exceeds 1,000 atmospheres. The darkness is absolute, the cold is relentless, and still, giants exist. Here lives Alicella gigantea, the supergiant amphipod, the largest amphipod ever discovered. Shallow water relatives measure millimeters. This one reaches over 34 centimeters. It scavenges endlessly, consuming anything it finds, gorging itself when food appears, then surviving for years without another meal. Some Hadal amphipods possess enzymes capable of digesting wood, an astonishing adaptation in a place with no plants. Occasionally, driftwood sinks all the way to the trench floor. These animals can convert it directly into energy. Even here, life finds a way. One of the most compelling explanations for deep-sea gigantism comes from an unexpected place: islands. On islands, isolation changes evolution. With fewer predators and competitors, animals often grow larger, a pattern known as insular gigantism. Scientists now believe the deep sea functions like a biological island. It is isolated, it has limited resources, it has fewer predators. After mass extinctions millions of years ago, many shallow water species moved deeper and diversified, adapting to new niches with little competition. Some grew smaller, others grew enormous. In this view, deep sea gigantism is not an anomaly. It is an outcome of isolation, stability, and scarcity combined. For centuries, sailors told stories of sea monsters, krakens, leviathans, creatures capable of dragging ships into the abyss. Those stories were wrong in their details, but right in their intuition. The deep does hold giants. They are not monsters. They are survivors. They are the result of physics, patience, and evolutionary time stretching across millions of years. Proof that life does not follow a single set of rules. What works in sunlight fails in darkness. What thrives in abundance dies in scarcity. And sometimes, the solution is not to shrink, but to grow. Despite decades of research, deep sea gigantism is still not fully understood. Why do some species grow enormous while others remain small? Is there a maximum size limit? Could even larger creatures exist, undiscovered, in regions we have never explored? We have mapped more of Mars than our own abyssal plains. Every time a submersible descends, it finds something new. And that may be the most unsettling truth of all. The ocean is Earth's largest habitat, and we barely know it. As temperatures rise and oxygen levels shift, the very conditions that allow gigantism may disappear, and the giants may vanish with them. We search the universe for alien life, but some of the strangest, most awe-inspiring organisms in existence live beneath our own feet, separated from us not by light years, but by water. The deep sea does not reveal its secrets easily, but every giant it reveals reminds us of something profound. Life is more adaptable, more patient, and more extraordinary than we ever imagined. And the deeper we go, the more we realize how little we truly know.